Bismillahirrahmanirrahim. Continue with thermoanalytical techniques. From this series of lectures on thermoanalytical techniques, I embedded my profile for the interest of anybody in the class. So one body can read first slide about my profile. So this slide is about the questions about DSC, differential scanning calorimetry. So this is a thermoanalytical technique in thermal analysis, DSC, differential scanning calorimetry. In this lecture about differential scanning calorimetry questions, as a template, various machines are presented in this slide, that is by the courtesy of Perkin-Elmer, DSC 4000, DSC 8000, DSC 8500 with autosampler, DSC 600 with autosampler. These are different designed equipment that perform DSC, and these are the manufactured by Perkin-Elmer company. The differential scanning calorimeter is a fundamental tool in thermal analysis. It can be used in many industries, from pharmaceutical and polymers to materials and food products. The information these instruments generate is used to understand amorphous and crystalline behavior, polymorph and eutectic transitions, curing and degree of cure, and many other material properties used to design, manufacture, and test products. While DSCs are manufactured in several variations, Perkin-Elmer is the only company to make both single and double furnace styles. We have manufactured thermal analysis instruments since 96 and understand application better than anyone in the industry. This is a well-renowned Perkin-Elmer company. In the following pages, we answer the common question about how a DSC works and what it tells you about the thermal properties of material you work within your laboratory. So what is DSC? The first question is what is DSC? Differential scanning calorimetry, or DSC, is a thermal analysis technique that looks at how a material's heat capacity (Cp) is changed by temperature. A sample of known mass is heated or cooled, and the changes in its heat capacity are tracked as changes in the heat flow. This allows the detection of transitions such as melts, glass transitions, phase changes, and curing. Because of this flexibility, since most materials exhibit some sort of transition, DSC is used in many industries including pharmaceuticals, polymers, food, paper, printing, manufacturing, agriculture, semiconductors, and electronics. In all the industries, DC is an important tool to characterize their properties. The biggest advantage of DSC is the ease and speed with it can be used to see transitions in temperature and material. If you work with polymeric material of any type, the glass transition is important to understanding your material. In liquid crystals, metals, pharmaceuticals, and pure organics, you can see phase changes are polymorphs and study the degree of purity in materials. If you are processing or distilling material, knowledge of a material's heat capacity and heat content changes called the enthalpy can be used to estimate how efficiently your process is operating. For these reasons, DSC is the most common thermal analysis technique and is found in many analytical, process control, quality assurance, and R&D laboratories. The next question: what is the difference between a heat flow and a heat flux DSC? The term differential scanning calorimetry refers to both the technique of measuring calorimetric data while scanning as well as specific instrument design. The technique can be carried out with other types of instrument. Historically, temperature transition in material were first seriously studied by ceramic industry in 800 using differential thermal analysis. This early work was done by placing a thermometer into a material and heating in an oven similar to way to meet thermometer is used. There were some serious problems with this placement of the thermometer was often not reproducible. This was done by SL Boersma's development of fixed thermocouple differential thermal analyzer. The analyzer of these designs are still common today and are called Boersma differential thermal analysis. A Boersma DTA can also be used to calculate heat flow with the right calibration and is also used for DFC technique. This is accomplished by measuring temperature difference and changes between a sample and a reference or the heat flux. These instruments are sometimes called heat flux DSCs. Like all DTA designs, the Boersma really measure the temperature difference T and calculate heat flow from calibration data. Because of their single furnace design, heat flux DSCs are less sensitive to small transition heat and cool at slow rate than heat flow DSC and give less accurate values for CP and enthalpy. The next question is, how does the difference affect me? For the vast majority of simple application, the data from both type of instruments are capable and both designs have strength and weakness. And if you are doing more than just looking at simple glass transition and melts, you may need one or the other. Some of the differences are given in the table. Heat flow versus heat flux DSC. Fast heating 250 centigrade per minute plus heat in heat flow is yes, while in case of heat flux, no. Modulated techniques, yes. In both cases, it's yes. Accuracy of CP values mean heat capacity. In heat flow, it's very high accuracy, while in heat flux is moderate. Delta H accuracy, that's all the heat content of the system. In a case of heat flow, it's very high, while in case of heat flux is moderate. Ease of cleaning is very in heat flow, while the moderate in heat flux. OIT testing, isothermal performance, that is moderate to excellent, while in this case of heat flux is easy and affected by the sample. So next question is, why do curve point in different directions? As shown in the figure below, this is a convention based on how the instrument work in a heat flow DSC. The endothermic peak, those events which require energy, point up because the minimum instrument must supply more power to the sample to give the sample and reference furnace at the same temperature. In heat flux DSC, the sample to absorb heat and to cooler than the furnace, so they point down. The reverse logic applies to the exothermic events where energy is released. The International Conference on Thermal Analysis and Calorimetry (ICTAC) said the convention that curves should follow this pattern. Many years ago, most modern software system let you flip the curve as you give. What is heat capacity? Heat capacity is the amount of energy as a unit of matter can hold. Think of a can of a green pea soup. It is a gelatinous mass at room temperature, but as it heats up in a saucepan, it becomes more fluid. Its heat capacity also increases, and a fluid soup at 100 degrees centigrade and hold more energy than the solid at room temperature. All materials show this increase in heat capacity with temperature. It is reported as either joule per gram, joule per mole, or calories per gram in the older literature. As heat capacity increases with temperature, the run of a real sample should show a slight upward slope toward higher temperature. There is step changes in the baseline across the melt as the heat capacity of the molten material is higher than that of solid. Lack of these features suggests some forms of data consumption. Of course, a strong peer will dwarf these features. Heat capacity may seem academic, but it turns out to have lots of practical implication and engineering often needed. For example, when running an extruder for polymeric or food product, knowing the heat capacity of the material can help you figure out how efficiently your process is and whether you are using too much energy. You can use it to calculate the energy needed to run a distillate or recycle column or to estimate how much energy is needed to keep something at a certain temperature. The standard is water with a heat capacity of 1 joule per mole, which means it takes 1 joule of energy to heat 1 cc of water 1 degree. Practically, people use fire as a standard as it is stable solid, so it does not change much or become contaminated. It can also be made very pure. This allows you to measure heat capacity and obtain very accurate numbers. The next question is, why is measuring the glass transition important? The glass transition has been called the melting of amorphous material and is unscientific as that is. It's an adequate description. Amorphous material such as glass has no organization in the solid state. It is random. This gives it the transparency that glass has. Among the other properties, as you warm it up, its heat capacity increases. At some point, you have enough energy in the material that it can be mobile. This requires a fair amount of energy compared to the baseline increase, although much less energy than the melting point does. This energy normally appears as step changes in the instrument baseline, pointing up in the heat flow instrument and down in heat flux. In non-crystalline and semi-crystalline polymer of any type, synthetic high polymers such as polypropylene and polystyrene, natural polymer like rubber, and biological materials such as protein, the glass transition is the best indicator of material properties. As the glass transition changes due to either different degree of polymerization or modification by additives, the physical properties of material changes. The relationship Tg to the degree of polymerization shown in the figure below change with these alterations. Similarly, material properties also change dramatically of the Tg. For example, material loses their stiffness and flow, as in case in molten glasses, and their permeability to gases increase dramatically, leading to increased spoilage in food products. Lyophilized material can collapse and their storage life is shortened as excipient drug reaction can increase. That can be shown in the figure. Assuming you know the calibration is valid and the baseline is acceptable, the transition should be clearly visible without excessive manipulations. If the peak requires multiple smoothing, it is difficult to detect from baseline noise or is exceptionally distorted. Another technique may be indicated. The next one, how can I improve my data? Data interpretation is very important in any type of analytical technique. There are several ways to improve a weak signal if everything else is working well. You can easily increase sample size by running a larger sample. You can run the same sample faster. You can use one of the more advanced technique which will be discussed later in page number 8, modulator technique or fast scanning techniques. You should remember that if you increase sample size, scanning rate or both, you need to watch for loss of resolution in your data caused by uneven heating of the sample. A large sample could ideally be run at a slow rate and a sample run at faster rate should be smaller. Both of these help because the heat flow is a function of sample mass and scanning rate. In some cases, a more specialized sample pan may be answered. Specialized sample pan exists for many purposes. Sample containing solvent can be run in sealed pans. Samples that evolve gases such as those containing explosive may run in vented pans. Films can be placed in pans that keep them flat. A different material sample pan may be needed to reduce interaction with the sample or to allow a hot temperature to be used. If you look in Thermal analysis supply catalog, you will see a wide variety of pan flowers out of specialized condition. One of the sample pans shown in the figure. The next question is, why does not my data agree with other thermal techniques? One common question is why DSC data does not always agree with other methods of analysis. This is most commonly raised with the different in values for the glass transition for DSC and mechanical methods of thermomechanical analysis and dynamic mechanical analysis. There are several reasons for this, but the most important one involves the nature of glass transition. The glass transition really a range of behavior where scientists have agreed to accept a single temperature as indicator per certain standard. Different industries have used different points from the same data set that can carry as such as 15 degrees centigrade. DSC, TMA and DMA measures different processes and therefore the numbers vary. You can see as much as 25 degrees centigrade in data from DSC to DMA data reported as peak of 10-year delta. The next question is, what is the difference between controlled and ballistic cooling? Cooling is often an underappreciated property of both DFC and material science in general. How a material is cooled from its melt defines its heat history, and the heat history can make a great deal of difference in a material's properties. The classical example is polyethylene terephthalate in PET material, which become nearly all amorphous when cooled rapidly from the melt but is mostly crystalline when cooled slowly. Since the heat history is so important in how a material behaves, the standard operating procedure in plastic is to run a cool heat cycle. The first heat shows the material has received the cooling step. If done with controlled cooling, impose the standard heat history on the material, while the second heat allows you to compare material directly to each other. Controlled cooling is important as you want the cooling rate to be controlled as the heating rate to get reproducible data. In controlled cooling, a specific temperature range per minute is specified as a rate somewhere between 0.1 degree per minute to 500 degree per minute, and should be maintained throughout the experiment. This is in contrast to ballistic cooling, where the sample is cooled as fast as possible by either cutting all power to the DC furnace or by removing the sample and dropping it into the liquid nitrogen. Very high rates of controlled cooling are desirable as some processes have rates of 800 degree per minute, and high rates allow you to model them. Controlled allows the greatest degree of separation between overlapping peaks and more sensitive than melting. Controlled cooling has also allowed you to isothermal crystallization studies to see how a material behaves when a process applies large temperature drop on a material. When the isothermal kinetic package, you can then predict behavior at rates that have not actually been measured. Why should I care about isothermal performance? Isothermal performance means the ability of the DSC to hold a precise temperature with no drift. This is best accomplished in a power controlled DSC as it is designed to control temperature. Many processes in real life are actually done isothermally: baking a cake, curing an aircraft wing, molding plastic parts, etc. Often the material is inserted into a set temperature region at a very different temperature. The cake goes from room temperature to 150 degrees centigrade, or the plastic goes from the molten state in the extruder to room temperature as a blown film. This means that DSC must not only be able to hold an isothermal temperature precisely, but it must be able to heat and cool to that temperature rapidly with no under or overshoot. This is another area where power controlled DSC has an advantage due to its design. The next question is, why do I study oxidative stability? Oxidative stability or oxidative induction time (OIT) test is often studied in both DSC and TGA. This is normally done by heating a material to a set temperature under inert gas and switching to air or oxygen. Once it has equilibrated, the time needed for the material to begin to burn. It's then recorded normally in a power compensated DSC. A flow through cover is used to remove the smoke from the DSC as quickly as possible. It can also be used to remove reactive gases generated by the sample. Often it is best to run these tests in a TGA as this experiment is very dirty and these instruments are designed to accommodate such samples. Next question is, when do I need to use HPDSC? HP means high pressure. High pressure DSC is used for several reasons. First, an oxidative stability test may take too long at atmospheric pressure to be convenient. An example would looking at antioxidant packages in motor oil. Secondly, some reaction from water and methanol as a byproduct leading to foaming in the sample. Higher pressure suppress this. Thirdly, some reaction kinetics are affected by pressure and running the reaction under control pressure is needed to study this effect. Finally, transition like the TG and boiling point are the responsive to pressure and running DSC under pressure. Allows you to study these processes for cooling point, boiling points. Pressure DSC also allows you to calculate the vapor pressure of the sample. When should I consider using UV-DSC? UV-DSC or photo-DSC is a DSC that has been adapted to allow the sample to be exposed to UV light. During the run, this can be done with the several types of light sources including mercury vapor lamps or LEDs over a range of frequencies and intensities. UV-DSC also allows the study of UV-initiated current system in the DSC such as those used for dental resins, orthopedic bone cements, hydrogels, paints or coatings and adhesives. It complements the technique of UV-DMA which allows you to gain mechanical information of this system. UV-DSC also allows you to study the efficiency of currying and to develop kinetic model for currying systems. UV-DSC is additionally used to study the decomposition of material under UV radiation. This can be for understanding the effects on the storage of pharmaceuticals, on antioxidant packages, polymers and rubber, on food property or on dyes in sunlight. It is possible to use kinetics to model the degradation by UV light. Because of high intensities of UV available, accelerator testing is possible. The next question is, how are kinetic studies done with DSC? Kinetic studies on the DSC can be done using scanning methods where the sample is either heated through a temperature ramp or isothermally where the sample is held at a set temperature. In the latter case, the ramp rate to that temperature should be as fast as possible to minimize the effect of ramp. The advantage of using DSC for kinetic study is it tends to better and more straightforward than other methods. The next question is, what is modulated temperature DSC? Modulated temperature DSC is the general term of DSC technique where a non-linear heating or cooling rate is applied to the sample to separate the kinetic from the thermodynamic data. This is a type solved in step scan DSC. This is done by applying a series of heating or cooling macro steps followed by isothermal hold. This allows you to separate the data into an equilibrium CP curve that shows the thermodynamic response of the sample and an isokinetic baseline that shows the kinetic response. Unlike some other techniques, these are calculated independently. This technique removes kinetic noises from transitions such as enthalpic overshoot or the current isothermal from overlapping TG. What is the fast scan DSC or hyper DSC? Fast scan DSC is the generic term of DSC technique that apply very high heating rates to sample to increase the sensitivity of a DSC or to trap kinetic behavior. Fast scan heating rates range from 100 degree per minute to 300 degree per minute, where hyper DC heating range from 300 degree per minute to 750 degree per minute. Heating at high rates was originally developed in power control DSC thanks to the small furnace mass, and the best results are still obtained in these instruments when the heating rates of 100 degree per minute to 750 degree per minute are applicable or applied. The response of DSC to to weak transition is enhanced, it is then possible to see very low levels of amorphous materials in pharmaceuticals, measure small amounts of natural products, freeze the occurring of thermosetting compound, inhibit the cold crystallization of polymer as well as the thermal degradation of organic materials. The next question is what hyphenated technique work with DSC? DSC is not normally hyphenated as frequently as is TGA, but hyphenation has been used. DSAR has been used to look at the evolved solvent from pharmaceuticals, while DCMS has been used to look at the composition of meteorites and the lunar rocks. DSC has also been coupled to FTIR microscopy look at the changes in a sample during a DSC run. The most promising hyphenated technique is DSC Raman, where a sample is irradiated by Raman laser as the sample is run in DSC profile. Because of the nature of the Raman spectrometer is ideally suited for this, as it does not require any processing of reflectance spectra nor the use of a special transmission path cell. DSC Raman shows great potential for the study of polymorphic material, polymeric crystallization, clean movement at the glass transition, and for the hydrogen bonding polymers. These are the questions about the DSC. Now you can see the glossary: annealing, calorie, crystallization temperature, dynamic mechanical analysis, differential scanning calorimetry, differential thermal analysis, endothermic events, exothermic events, fast scanning DSC, glass transition, heat capacity, heat history, heat of fusion, isothermal kinetics, joule, melting point, morphology, quench cooling, scanning, specific heat, startup transition, transient temperature, TGA, thermogrametry analysis, thermal mechanical analysis, and watt. For the further study, the additional reference can be seen. And thank you very much for your alertness and patience.